So hello everyone. Last time we talked about Eisenstein's criteria, and we say that if p of x is a polynomial, say a0 plus a1x plus till an x, and is a polynomial over z, and there exists a prime number p such that p divides the coefficients a0 till an minus 1, and p does not divide an, p square does not divide a0, then p of x is irreducible over q. And today we are going to prove this theorem and take another two theorems to end the chapter 9. After that we are going to work in chapter 10 in the next video. Divisibility in an integral domain. We will talk about integral domains, divisors in integral domains, irreducible elements, a little bit about the field of fractions, Euclidean domains, unique factorization domains, and more stuff. So we'll start with the proof of Eisenstein's criteria. Suppose that p of x is primitive and reducible over q. Now we can always suppose that p of x is primitive. We're working over a field. Why? Since if p of x is not primitive, we can write p of x as c1 p1 of x, where c1 is the content of p. Now p1 of x is a primitive, we can work over p1. The irreducibility of p1 is equivalent to the irreducibility of p. That's an exercise we are going to solve later in our exercises. So in exercises set 4. So the irreducibility of alpha p over a field is exactly equivalent to the irreducibility of p over the same field. So no problem, we can always assume that p of x is a primitive. Now we will assume the contrary of our result, that p of x is reducible over q. So can be written as reducible over q and primitive then by Gauss lemma. We can find that p of x can be factorized into product of polynomials in z of x. So it can be written as something like b0 plus brxr times c0 plus del csxs x power s. These two polynomials are in z of x, of course, and both r and s are less than n. Now now we have p squared does not divide a0. A0, if you expand, is equal to what? B0 C0. So this implies that p squared does not divide B0 C0. Okay, but we know that p divides A0. So p must divide one of them, even either P0, B0, or C0, but cannot divide both, since if p divides both B0 and C0, then p squared divides A0, which contradicts our assumption on p. Now we choose, without loss of generality, that p divides B0 and p does not divide C0. Now an also is equal to brcs, and p does not divide an, so p does not divide br and cs. Does not divide br and cs. Now since p does not divide cs, p does not divide c0, we can talk about the smallest element. Let m be the smallest integer, so take m be the smallest integer, so that p does not divide cm. Look over the term am. Am is equal to what? B0 cm plus am, after expanding, after multiplying these two polynomials, you find that, and comparing with the initial expression of p of x, you find that am is equal to what? b0 cm plus b1 cm minus 1 plus till so increase b by 1 and decrease m by 1 till bm c0. Now uh, this term here is divisible by p, since p divides v0, but these terms here on the left are not divisible by p. So we conclude that am is not divisible by p. All this term here, am, is not divisible by p. Now am is not divisible by p, then am is equal to an. Then, since the only coefficient in p of x is not divisible by p is an, this means that m equal n. A contradiction. We cannot. So yeah, the smallest integer so that p does not divide cm is cn. Okay, not c0. That's a contradiction. So our assumption on the reducibility of p over q implies a contradiction, and so p of x is irreducible over q as required. Another theorem. If f is a field, then f of x is a principal ideal domain. What do you mean by principal ideal domain? Means that f is an integral domain, f of x is an integral domain, so that every ideal in f of x is principal. What do you mean by every ideal in f of x is principal? So f of x, every ideal in f of x is generated by one element in f of x. Can be written, so I can be written as an ideal generated by f of x for some f of x, of course, in the ring of polynomials that you are working over. So, proof. Let I be a non-trivial ideal. So, this ideal and p of x, take p of x belong to I, a non-zero element, of course, of minimal degree. If p of x is equal to constant, then I is equal to 1. So I is cyclic. Nothing to show. So we will suppose so that degree of p of x greater than or equal to 1. If degree of p of x greater than or equal to 1, and take that and take f of x in I, then f of x can be written as we know, q of x, p of x, plus r of x. Okay, so this is the division algorithm. Now, if r of x equal to 0, nothing to show. Then then I is generated by p of x. If r of x equal to 0, nothing left to show. We conclude that I is equal to p of x. If r of x is not equal to 0, then r of x is not equal to 0 implies that r of x equal f of x minus the q of x, p of x. This is an I. This is an I also. So r of x is an I with degree from division algorithm of r of x is less than degree of q of p of x. That's a contradiction. We find a non-zero element an I of degree less than strictly the degree of p of x, which is the minimal minimal degree, and this is a contradiction. So no case that r of x different than 0. R must be equal to 0. R of x must be equal to 0. And so each ideal in this field, in this ring here, f of x, is generated by the non-zero element of minimal degree in I, and so it's cyclic. And f of x here is a PID, a principal ideal domain, when f is a field. Okay, so the importance that f is a field arises from using the division algorithm. We know that we cannot use the division algorithm unless we are talking or working over a field. So this theorem happens only if f is a field, and we will give an example where f is not a field and f of x is not a principal ideal domain. We will give an example in exercises, and we will show that z of x is not z, even though z is an integral domain, but it's not a principal ideal domain. We will show that this is not principal. We will show this later in exercises. Now, the final theorem before ending this chapter, very important theorem also. We will use this theorem proving the fundamental theorem of fields later on in the chapter 11, I guess. Okay, so we are now in chapter 9. The next one about the divisibility in integral domain and Euclidean domains and the unique factorization domains. All these stuffs are to be discussed in chapter 10. After that, we are going to start with finite fields, with fields, and then we are going to discuss the structure of finite fields and go ahead in Galois theory. Now, this theorem says that let f be a field, of course, and p of x belong to f of x. We have the ideal generated by p of x is maximal if and only if p of x is irreducible over f. Here is the proof. So first, suppose that p of x is maximal. So suppose that p of x, this ideal here, is maximal. We need to show that p of x is irreducible. So start p of x, let p of x equal f of x times g of x. We need to find that one of them is a unit polynomial. So we conclude that p of x is irreducible over f, where these two polynomials f of x and g of x, of course, are in f of x. Now, fx gx, this product is equal to px, belongs to p of x, and we know that every maximal ideal is prime ideal. So product of two elements belongs to prime ideal implies that one of them, at least, we suppose without loss of generality, that f of x, so without loss of generality, that f of x belongs to what? To p of x. Now f of x belongs to p of x. This means that f of x is a multiple of p of x, of a multiple of p of x, and so p of x, why? Since we know that f of p of x, the degree of f of x is less than or equal to the degree of p of x. And here f of x belongs to p of x means that f of x is a multiple, must be a multiple of p of x, cannot be a polynomial of higher degree. Okay, so or even a lower degree, So f of x is a multiple of p of x. P of x, this field, then this ideal is subset strictly of f of x, which is a contradiction. This contradicts the fact that our ideal is maximal. They cannot be, they are equal if we assume that one of them are not is unit. If f of x and g of x is unit, one of them is unit, then p of x equal f of x. Okay, so there this no contradiction here. But assuming that both these polynomials f of x and g of x are non-units, then they are the degree of f of x in a case must be lower, and a case must be greater than or equal to the degree of p of x. That's a contradiction with the maximality of the ideal p of x. Now, to prove the converse, suppose that I is generated by, sorry, p of x is irreducible, and let us show that this polynomial, this is maximal. Suppose that p of x is subset of I, subset or equal to I. Now I can be written as, since we showed this in the previous theorem, that if f is a field, then f of x is a principal ideal domain. So I can be generated by one element and f of x. So I is the cyclic. So I is cyclic. So now this, our ideal is subset in I, then p of x in I. So p of x can be written as f of x times g of x. But p of x is irreducible. That's our assumption. P of x is irreducible, then one of them is a unit. If f of x is a unit, then I is equal to r to f of x. Okay, if f of x is a unit, then I, which is equal to f of x, is generated by a constant, and the ideal generated by a constant is the whole ring. Now, if g of x is a constant, then f of x must be equal to p of x. Okay, two polynomials different by a constant, non-zero constant, have the same generates the same ideal. So the ideal generated by f of x is equal to the ideal generated by p of x, and this implies that I is equal to p of x. So whenever this ideal is a subset of I, implies that even I equal p of x or I equal to f of x. This establishes, in fact, that p of x is maximal as required. See you in the next video.